Okay, so we have all kinds of different load models that we use in the study of structures. They're from an external load standpoint, they really boil down to a class of two different types: concentrated effects or concentrated loads, and loads that are spread out, or what we call distributed loads. Right? That's just distributed is just a fancy way of saying spread out. What you have up here is a representation of actually both. We've got the applied external forces that are spread out such that the intensity here at the far left is 610 newtons per meter. That's like a velocity. It doesn't mean that if we have a meter of it we'll have 610, but if it were to remain at that intensity for every meter, we'd have 610 newtons. Just like 30 miles an hour doesn't mean that you're going to go 30 miles, but if you were to keep that velocity for an hour, then you would have gone 30 miles. Right? It's an instantaneous intensity. Down here at this end, we do have over this longer stretch the same intensity of 370 newtons per meter. So the units of a distributed load are force per length in that overall intensity. Now, I said that we actually have an example of both. If I get out my magic scissors and I remove the support at B, then I'll have a concentrated force that represents the reaction at B. Right now, in reality, there is no such thing in real world of a concentrated force. There has always got to be some finite area here, that's the contact area, that is going on to transfer that force. There must be. But we pretend as though that contact area, that delta x width, or delta area if you prefer, either one, goes to 0. Right, in the limit of that. That's what makes it a concentrated effect. Right? Same thing over here at A. We've got, then pull the pin, we've got a y and we've got a x. Right? Always thinking in terms of, in the end, our global coordinate system, and we're going to stay in 2D. We've got translation of the x, translation of the y, and some sort of rotational kind of thing. Right? That's key when we come back and talk about, well, the resultant of a distributed load, and there's a phrase up at the top of the page that says, well, that passes through the centroid of the area that represents this distributed load. Well, this area, that's what this is. This is just a diagram. It's not real. It just represents, it's symbolic of, and if we have an intensity over here of 610 newtons per meter, and we set a scale, draw it that high, there, 370 here, then this outline shape, well, that total area is going to represent the total force. Right? So for instance, in this little segment here, 370 newtons per meter over 3.6 meters, oh, well then I can find out what that total force is. Right? And that total area, that total force for that resultant is really going to, in a sense, preserve or have the same translational effect. And we must do that. But we have to also have the first moment of the area. Again, this area is just, it's not a real area. It is just the area of the representation of the forces. That first moment of the area is going to preserve or have the same rotational effect. right? And this whole notion of the total area gives us the total force. We're going to have the same first moment of area. Remember, that's how we find centroids of area, that the centroid of an area is equal to the first moment of the area. We give that the symbol Q and divide by then that total area. Right? In other words, that's why the resultant of the force of a distributed load passes through the centroid of the area that represents the distributed load. Right? What that does for us is it preserves both the translational effects and it preserves for us the rotational effect of that force. So let's see how this plays out in much grander detail. Right? We've got a reaction at the left, a y and a x. We have a reaction at the roller. Let's see, this is not exactly at the same scale, so I need to pull this over just a little bit. There's by, right? And the distances involved, right? 6.6 plus 1.8 is going to be a distance between those two of 8.4 meters, right? And I can look at this area up here as being broken apart into a rectangle and a triangle. The rectangle is 370 newtons per meter high in its scale, and the little triangle has a height then that is 610 minus 370, or that's 240 newtons per meter. This rectangle has a length of 6.6 plus 3.6, or 10.2 meters. Its centroid then would be halfway along at 5.1 meters, and then the triangle, of course, is at the 1/3, 2/3 location of the 6.6 meter distance, so it's over at 2.2 meters over. Okay, so now with that we can think about representing what's going on here. That these forces, distributed forces, will act as though, from an external static equilibrium standpoint, as though they act through that centroid of that area representing them. So we can do summation of moments about A, and we'd have 8.4 meters times by, and then minus then our others here. We've got 1/2 of the height, that's 240 newtons per meter, times the base, that's 6.6 meters. Check out the units. Meters dividing into meters, giving us units of force. This would be the total force of that triangle. Let's even just work that out here. 240 times 6.6 divided by 2 is 792 newtons, right? And its moment arm is 2.2 meters. That's this one here. And it's going in a clockwise fashion, so that's negative for the equation. And then we've got the rectangle down below. That's 370 newtons per meter, running for 10.2 meters. So that would have a total of 3774 newtons. Its moment arm, with respect to A, is 5.1 meters. So that's good. I have Newton times meters. That would be our units of moments. We'll set that equal to 0 for equilibrium. Right? And now we can solve for our by value, which will be 1 over 8.4 meters times 792 newtons times 2.2 meters plus 3774 newtons times 5.1 meters. And let's see what we've got here. we've got an answer for By that is 2498.8 newtons. Check out the units, Newton meters here in the numerator divided by meters in the denominator. And of course you know that that's way too many digits. Doesn't start with a 1, so we're going to end up with 3 digits here. So By would equal, this would round up to, effectively, let's convert this over here. This is times 1 kilonewton per 1,000 newtons. So that would be 2.4988 kilonewtons. And now rounded to the appropriate 3 digits, we get an answer that says that By is 2.5 kilonewtons acting up.